Okay. Continue. Okay. So this force is always normal. This isn't a box. I'm just drawing the right angles over here. It's always normal to the surface. That's why we call it the normal force. Because if you remember from Calc 1, we got a normal vector, right? This normal vector is a perpendicular vector to the surface. If your surface is like this, over here, the normal vector would be perpendicular to that little infinitesimal area that it's coming out from. Over here, the normal vector would point this way. It always stays perpendicular to the surface, right? And of course, if it's a curve, we just take it as an infinitesimally small area that the vector's rising from. So this is called the normal force. Now, there's different types of forces. This type of force is a contact force, right? It means that for this box to feel this normal force from the ground, it has to make contact with it, right? Friction is another contact force, right? There needs to be contact between itself and the ground to have a force, to feel the force. Now there's non-contact forces. Can anybody give me an example of a non-contact force? And hint, it's one of these two forces.
Electromagnetism.
Well, yes, electromagnetism is a non-contact force. What else? Anything else? So if you jump out of an airplane, right, you're experiencing acceleration. What force is providing that acceleration?
Gravity.
Yep. And then are we in contact with the Earth or in it?
No, but there's
Nope.
air resistance as well.
Yeah, air resistance is different, and it's in the opposite direction than the free fall, moving downwards. So gravity is another non-contact force. So so you can break up these forces into different categories, and then you can even do a subgroup. What are the normal forces? There's different types of normal forces as well. Right.
Professor, how about magnetic forces?
That's non-contact, right?
Okay.
Yeah. So gravity. So the difference between gravity, gravity and not for you lump gravity and magnetism or electromagnetism into one group. The difference between those two and everything else that we push is that everything is basically that we experience in real life is derived from those two non-contact forces. It's just that we don't see it. So by us pushing on an object, what's happening, or I push on this board, the reason why my hand doesn't go through the board is because of electromagnetism. The atoms come into close contact with each other, and there's a force that repels each other. So we don't, my hand doesn't go through other matter. And this is generally caused by electromagnetism. So friction is an electromagnetic force. So in addition to this repulsion, there's actually an attractive force between the atoms, and this gives rise to friction. Right. So, okay. Okay. So let's do example. Let's do example 4.3. Erase this. So in this example, where we have a box, actually a gift that my friend has given me. Right? And we want to determine the weight of the box and the normal force exerted on the box. There's a mystery surprise inside, and we want to see what it is. So we want to weigh it, right? So let's analyze the problem. So the first step is to draw a diagram. And here's the gift box, right? That's the wrapping paper. Right, this is the gift, right? Now we draw the forces on the box, right? And I'll draw the forces where they originate from. Generally, we draw them from the center point, but we could, if we want to express something differently, we could have the forces start someplace else. We could translate it. So the force due to gravity is downwards. This is mg, right? And I draw it from the middle because it's acting, gravity's acting on the whole object, right? Now there's a contact force, the normal force, and we'll draw that from the surface that it makes. It's an equal and opposite force. We'll try to draw it the same one. So right over here. Okay. It's hard to see, right? Draw it in blue. Better. If there's any issues with seeing the writing based on the colors, just let me know. Just unmute your mic and let me know at the time, and I'll fix it. Let me see if the lighting helps. So, and this is the normal force, Fn. Right, and this occurs at the ground. Now, let's calculate the net force, right? So let's determine the weight, right? So this is in a static position. So what I mean by static is that nothing is moving. It's not experiencing any acceleration, right? So, and so far, if it's just resting on a box, there's no net acceleration in this direction. So let's label our axes. This is X and this is Y, right? So the net, so now we write down the components. So the net force in the X direction, let's do the X direction first. And there's no forces in the X direction. So this is 0, right? And this is equal to acceleration in the X direction. So this implies that this is equal to 0. This does not help us. We can't find the mass of this object through here. Okay? Now, let's see what's happening in the Y direction. So the net force is still 0, but we know the forces involved in this. So there's more to this than meets the eye. We'll have the 0, and then we'll have Fn minus mg, right? And these are in the Y direction. They're equal and opposite. We know that's 0. We know that this is 0. And based on this, we know then that the normal force is equal to the mass times G. So if we can measure this normal force, we can determine the mass of the object. And this is basically what a scale does, right? So the mass is just the normal force divided by G. Now you may think this is trivial, right? Oh, we know that we already know that it's the normal force is equal to the mass times G. So this is obviously true. What's the point of this, right? Well, if we apply another force, this will change Fn. So this does not always hold. This only holds if we have these two forces here, right? If we apply a second force, right? Let's say if my friend pushes down on the box. Let's say if I push down on the box, right? Let's say when this is 40 newtons. So I push down on the box at 40 newtons. Right, this is part A. And then let's calculate what the net force and everything will be. F of x remains the same, and we know that the box is still not moving. We can't push it to the ground, but not that strong. So this means that F of y is equal to MAY, which is equal to 0, and it's equal to the sum of the forces, right? So it would be the force, the normal force pushing up minus mg, the force due to gravity, and minus another 40 newtons that I pushed down with. So now we'll have the normal force in more, plus 540 newtons, right? So now we can get an idea of, we can actually calculate this normal force. And then what a scale does is just measuring this normal force. So we have the platform that provides the normal force on the object that we measure. And then over here, it's on either some springs or or a digital accelerometer, right? And we can measure this force by measuring the displacement on this spring, how far it moves up and down. And then we can determine the normal force because, right, then this exerts a force downward on this object based on Newton's third law. We know that the springs have to push up an equal and opposite force to stop so that it doesn't move. So that equal and opposite force is the direct measurement of the weight of the object or the gravitational force. So we kind of use Newton's third law to kind of relate this force, the force due to gravity, to the normal force on this object to the normal force on the springs, and then we could say with mathematical certainty that the force on the spring is the same as the force on the box. Right? Now, in this example, it says, now what happens if we lift up the box, right? What happens to this normal force? Well, in this case, for part C, let's erase this. For part C, maybe I'll write it in a different color. For part C, now the force is upwards. So this is B. And this is C. So now if there's an upwards normal force, I mean, an upwards force that we're pulling up on the object, right? So this equation remains. Now F, the 40 newtons is upwards, plus 40, right? And then when we solve for Fn, we see that this is subtracted from its gravitational, the force due to gravity. Right here. Now, so that means that the normal force is less, which makes sense because we're lifting it up and we're applying a normal force. So now let's do a problem with this. Let's do another problem with this, I mean. So let's say if we want to lift up this box, right? This would be seven. So let's say if we lift up this box, we have a rope, a piece of rope. Tied around this box. Right? And we lift it up with this rope. We got a hands wrapped around it. And we lift it up. Right? And let's say there's no ground and we're just lifting it up. Right? So first we have a force due to gravity. Then we have a force due to the string that we're lifting this object up with, right? And this force we'll call FP. Now, I'll mention it here. So the force provided by a string is called a tension force. So this rope or string connects the force exerted on my hand to the box. And this tension force is always along the direction of the rope at the point where it leaves the object. So here, the tension force is going upwards. So the tension force on the box is going upwards because that's where the rope is connected to. And and we could use this to translate forces from, so if we have like let's say if we had a pulley and we have a string attached to the mast, right? And let's say it's connected by my hands over here, right? This tension force can translate a force from the Y direction to the X direction. Because over here, the tension force is this way. And over here, the tension force is upwards, right? And it's just translated through this rope, the force exerted by the fibers in the rope. So we could use the ropes to kind of couple two objects together in this way. Anyway, so back to this problem. So Now, let's say the box weighs, the mass of this box is 10 kilograms, right? Now, what happens when this person pulls on this box upward with a force that's equal to or greater than the box's weight, right? So let's see. So the net force on this box, remember from last time, is, so this is FP, is equal to the normal force, whatever the normal force occurs from, plus minus the force of gravity, plus this force of pulling, we'll call it FP. All right. And then in this case, the normal force is 0, and this is equal to MA. I'll write down here. And then this is just equal to MA in the y direction. This is 0. So we're left with this. All right. And what we find is that when this is 0, let's say if it's equal to each other, this would be 0. All right.
Professor, I have a question.
Yes.
So gravity is a force, or is it going to be acceleration?
It's a force, and it provides an acceleration.
Oh, okay. Okay, makes sense.
It provides the acceleration. So when we talk about when we say acceleration due to gravity, right? The force due to gravity can be different for different objects, because the force due to gravity is equal to this. It's related to the object's mass, right? So the bigger the object, the more force there is.
Okay.
Acceleration due to gravity does not change.
Non-point, basically.
Yes, that's why we speak about the acceleration due to gravity, because no matter what object you have, it's always the same. This is an approximation. We'll actually go into the actual calculation of the force itself. But for all intents and purposes right now, just assume that the acceleration is, for every object, is the same at 9.8 seconds squared. So that's why we use acceleration due to gravity a lot, is because this quantity does not change depending on which object we look at, right? So we could just say, so this is just a common standard, right? While the force is dependent on the object. So, good question.
Professor,
Yes.
the bottom, the arrow that looks down, is it represents the vector of force due to gravity?
Yes, yeah, it is. Let me write it. Let me add that in. Yeah, Fg is equal to. Yeah.
Thank
you. We'll put the arrows in there. Right. So now we have this equation where the two forces are equal to each other, right? And then, of course, they equal and opposite. If we look at this equation, we can see that they equal and opposite in this format, right? We include that sign over here. Now, if this force gets greater than Fg, that means that this does not add up to 0, right? So if Fp is larger than Fg, let's write in the case over here. So this is for when it's equal to each other. If that's larger, that means that we'll have this situation is equal to some finite acceleration, right? So let's say if we have FP of 100, let's say this is equal to 100, right? And then we know the mass, right? So we can calculate this. So this would be 100 minus the mass, which is 10 kilograms, times the acceleration, 9.8, right over here. And then this is 10 times the acceleration, and we could calculate, we could figure out the acceleration. Here, this is just 98. So then we have 2 divided by 10, and we find the acceleration to be 0.2 meters per second squared. Okay. And this is how we'll be doing all these equations for now. And so this is called, when we draw a diagram like this, we call this a free body diagram, which means we draw the object by itself, and we draw its forces associated with it. And the way it connects with the outside world is through these forces. All right. So let's do a problem in more than one dimension. I want to look at, well, yeah, I guess we'll do this one. So let's say we're in a canal, and when you're in a canal, right, it's very narrow. And what ends up happening is that you don't usually operate the propellers on the boat. And there's usually a pulley system involved, where on each side, you have people pulling the boat, right? Now, you don't want the boat to go side to side. You want a force that's completely in the X direction, right? We'll draw the X like this. We want to force in a horizontal direction in this case, right? And let's say if we have two forces, right? And then this force, we have A over here that's pulling on the rope, and B over here. And then FA is equal to 40 newtons. And FB is equal to, what is it, 30 newtons, right? Let's figure out the force on this boat. Now, let's draw a free body diagram of the boat. So we'll just draw vectors. We don't even need to draw this boat. So let's say the boat is at the center over here, right? The forces at this point are FA, right? And FB. These are the two relevant forces. There's actually also forces in this direction, in and out of the board, right? It's gravity, and then what's called the buoyant force. And this is the force that allows the boats to float, and this is from the displacement of the water. So we have these two forces canceling out. So there's no motion. We're assuming that there's no motion in and out of the page, right? So it's these two forces that are pulling on the boat, right? Now, now let's calculate the total force in these two in y and x direction, right? And for this, we need to sum up the vectors, right? We need to break it down into their components, right? This is FAY, FBY, and then we have FAX and FAY. Right? And these are the four components. So we have to break the forces down into each of their components and then sum them up. Right? So let's do this for the x, the sum in the x direction, right, is equal to FAX plus FB. This should be a B over here. FBX, right? And then we just use the cosines to do this, right? So we're given this angle. So now let's relate the angles, right? This is 45 degrees to this line. So that means that's 45 degrees. So for x, we use cosine 45, right over here. So this is just the total force, FA, times cosine 45. Right. And then over here, we're given this angle, which is 37 degrees. If you remember, all students take calculus, we can figure out what's positive and negative. Take calculus. We're in a C, so this is cosine, right? Because this is the leg that's adjacent to the angle, right? The x is adjacent to both of these angles, so we use cosine. You see that's positive in that direction. So we can keep that as positive. And now we know that the forces add up in this direction. This makes sense because it's both are pulling along the same x direction, right? So they add up. Now for the y, we have this, where we just add up the y direction now. Okay. And this is sine, because now we're working with the opposite, with the side that's opposite to the angle that was given to us. Right? This is the angle given to us, so that's sine. If we were given this angle, we would reverse it. This angle is next to the y component. So for this one, if we're given this vertical angle to the y-axis, then we have to flip it and use cosine over here. Right. But for now, we just need sine. So sine 45. And then we look over here, right? From all students take calculus, in the fourth quadrant, sine is negative, right? So then and this is obvious, it's in the opposite. The y force for B is in the opposite direction of x. If you call is in the opposite direction of A. So then, if we call the A force in the y direction positive going upwards, then B would obviously be negative, and this agrees with our sine function. And then we just plug this in. We're given these numbers. This is 30 newtons, the magnitude, and this is 40 newtons. We plug it in. And you can look at this example this is example 9 now. If we look at the answer, The resultant force will be 22.3 newtons in the x direction. And then it would be 10.2 newtons in the y direction. Right? So eventually the boat will be tugged upwards, right? And I kind of drew the picture by accident that way, right? It's being pulled that way a little bit, right? That's not exactly ideal. So the person pulling on this side would want to adjust his angle so that these forces would cancel out. When would that occur, you ask, if you ask? Well, then all we have to do is to set this force. So what angle does this have to be to make this 0? We'll call that theta B for Fy to be 0. And how would we do this? So if we want to find the angle at which the force in the y direction is 0, how would we do that? Anybody?
We're trying to find the angle, you say?
Yeah. Okay. So right now there's a force in the y direction, right? It's actually being pulled upwards. We want to adjust. Our angle at B so that there's no acceleration in the y direction. So we want to adjust this angle so it doesn't move to the side of the canal. Well, no, not exactly. If we make this 45 degrees, this is not going to be equal, right? The sines will be equal. These will be equal, but the forces don't necessarily have to be the same, right? If these are two different people pulling it, right, they're not going to always have the same force that they can apply, right? So the more general equation is we take this one and we just substitute this for theta. So we'll have sine 45, we'll keep this angle constant, minus FB sine theta. Now the critical part, what's the total force if we don't want any acceleration in the y direction?
0.
0. So then we set this to 0, and then we can find our angle. So we find that sine theta is equal to this ratio, sine 45, right? So given these two quantities, we can find this angle that we need to satisfy. And then we can plug this angle into our x to see how fast we could, how much force we could apply in the x direction accordingly. And we can optimize these problems accordingly, right? To increase the speed as much as possible, but we won't go that deep into it. And then if we want to calculate the resultant, we just do a vectorial analysis, right? If we want to find that, let's say this is our resultant vector, back to this, and we want to find the FR, the magnitude. This is just the two components, and we the square root of the sum of the squares, Pythagorean theorem. Right. We have that, and then tan theta is just the ratio of the two components, and this gives us the angle of the resultant.